Physics 2018, this is Mr. Lewis. We're going to finish part 3 of the Unit 5 study guide. I was doing part of number 18 in the video before this, so I already talked about this, but I'll quickly summarize. So we said that with Stan here, with his spring-loaded cannon, he's going to take all of that elastic energy stored up in that spring cannon and turn that all into the kinetic energy, which will get him his launch speed. So to answer this, whose bubble have the higher launch speed, that's how you'll figure that out. You'll use elastic energy equals kinetic energy for the launch. Then I'm going to have, I need to add the little, there we go. So this is for Jan. She is going to just do some proper work, literally just throwing it. So she is taking her energy and putting it into the ball. That's what work is. Remember, it's a mechanical transfer of energy. And we know that work, in one of the equations, one of them is force times distance, the other is change in kinetic energy. So since we want to know final speed, that kinetic energy one sounds real enticing. So let's use that equation. Work equals change in kinetic energy. That's how we're going to find the velocity for Jan. So let us continue with what we were doing. Let's label these for what they are, Stan and Jan. So let's put my little divider line that I like to use. At least as of today that I like to use. So EE equals KE, so we got our 1/2 KX squared, KX, and I want control period per squared, equals 1/2 MV squared. So quick thing here. So remember I told you before that you can cancel out M's if there's an M in every single term. We don't have that in this case. So we can't cancel out the mass this time because in the other side there is not an M. So this is one of those times where the mass is actually important in a conservation of energy equation. However, what we can do is there's a half in both of these, so the half basically doesn't matter. So I can just delete those because they cancel out. So kx squared equals mv squared. So this information that we know from the problem, let's use that. So I'm going to hit the enter key, tab over to that section there. Let's do K is going to be that total of the elastic constant over here. It's 15,000, so let's put that 15,000 in right there. Why is it fonted like that? I already said that I hate doing this on a typing machine. I'm very tired, I'm sorry. So 0.75 is going to be our compression of the spring. Remember, that's what X stands for. If we go back up to the formula sheet, it tells you that, and I did that in the video before. You can go up and look yourself. 0.75 is going to be our X value, so 0.75, and I want that to be squared. That is going to be equal to the mass of 3 times the velocity that we don't know squared. So to get that final velocity, we're going to say do some algebra. So 15,000 times 0.75 squared, if I do that in my calculadora over here, then... No, that's not what I want calculator. Here we go. So calculator says 15,000 times 0.75 squared. That's going to be, ew, so 8,437. That's an ugly number. And then we're going to divide that by 3, because we got that 3 on the other side, so let's just do that now, divided by 3. That equals, so we've got tab, 2, 8, 12.5 equals v squared. I'm aware that I skipped some steps. If that bothers you, remember, I will show you some algebra anytime that you want to see it, but I really hope that at this point you got your algebra down. If not, please, please, please go to your math teacher and do some extra algebra practice, or come to me. I will help you as much as I can to try to teach you how to do some basic algebra. So square root is the last thing that we need to do because we need to get v by itself, and there is still a square on there. So to do a square root of 2812.5 is going to give us our final answer. So v equals, I'm going to put a little subscript here, v stan, because that Stan's final velocity. So this is going to be the square root of 2812.5. Turn the phone sideways, clear it out, move out of the way. Square root 2812.5 is going to be equal to 53.03 meters per second. Now, over here with Jan, we have a similar situation. So let's, no, don't do that. Divider line. So in this case, we're going to use, I'm going to hit enter here so we got some extra space in between those 2 points. Work equals change in kinetic energy. So, well, it's not change in kinetic energy, it is the kinetic energy. Because originally, the ball was not moving. So you throw the ball, it starts from a velocity of 0. The whole change of the kinetic energy is going to go all the way up to, well, the final kinetic energy. So the work done is going to be the kinetic energy if you start at 0. So if the change is starting at 0, then it just equals the kinetic energy. That makes it a whole lot easier in this case. So work was 30,000. That's just straight up a number. And that work value that we got, by the way, just to show you, work, see, 30,000 work. And 30,000 is going to equal, again, 1/2 mv squared, because that is still the equation for kinetic energy. But this time, we have a slightly different setup. So enter tag down here. So I'm going to plug in what I know. 30,000 equals 1/2 times the mass. It is still 3. That has not changed. And then I want my v squared. So 1/2 times 3 is 1.5, so I'm just going to do a 30,000, wow, 30,000 times 1.5. Nope, not times. That is not what I want to do. So let's just simplify here, right here. 30,000 stays as it is. Then you do 1/2 times 3 is 1.5 v squared. So now I'm going to divide by 1.5 because that is the opposite of multiply. It's 1.5 times v squared right here. So opposite of that is divide. So 30,000 divided by that. 30,000 divided by 1.5 equals, that was stupid. I should have known that right off the top of my head. That's going to be 20,000. 20,000 equals v squared. Now, right here, I don't even need to finish this problem because, as you can see, 2,812 equals v squared, and then 20,000 equals v squared. This one's going to be bigger. Jan wins, but just for the sake of completion, what is the square root of 20,000? V for Jan is going to equal the square root of 20,000. Let me get that on the calculator. The square root of 20,000 is 141.4. That is handily higher than Stan's initial velocity, launch speed. So her arm is a cannon unto itself compared to this actual cannon. Spring-loaded cannons, not near as good as real cannons, and especially not as good as Jan's throwing arm. Good lord, I didn't realize that I made this problem so lopsided. Anyway, so Jan clearly wins. She is the victor in this particular case. That is meters per second, not milliseconds. Bold. She's the answer. Jan wins. All right, moving on. Okay, now I'm on to all the simple machines, but I told you I would do all of. I'm not going to be able to get them all in one video, so let's just see what we can do here. The wedge. All right, first of all, make sure that you're checking and making sure that you have the correct mechanical advantage equation for the machine that you're looking at. The wedge one is right here. It's length from the flat to the point, not the diagonal, divided by the thickness. So if I look over here and zoom in on my wedge, let me try to do that here real quick. Let me just zoom this up. There we go. So the length, it shows you it's not measuring along the diagonal. It's not going sideways. This is just a straight up all the way across from the flat edge here to the point. So like literally, if you took the ruler and lined it up horizontally, it would go straight across here from the point to the back. That is the length that we're talking about. And then the thickness or the width, that's going to be this side, the flat side. It's always the side that you push from. You push the force into the back of the wedge. Imagine that's an axe, like I had some of the groups point out. The handle would be here at the back, here on this side. So the thickness is always going to be that side that you're pushing from. All right? It doesn't matter whether it's a skinny wedge or a fat wedge. Whichever side you push from, that side is the thickness. So let me fix my picture. So, wedge. I'm going to copy my equation. So, back where I was. I'm sorry for scrolling so much. So, what is the IMA of this wedge? Well, the IMA of a wedge is equal to length divide thickness. That's my equation. And then I want to say that IMA equals the length, it tells us in the problem, length of 0.7. So, bam, there we go, 0.7. Divided by the thickness. 0.2 meters wide, tells you right there, 0.2. This is the main reason I want you to write down the equations every single time, because if you write these upside down because you weren't paying attention, that will mess you up. So length divide thickness, 0.7 divide 0.2. Don't do them upside down because I guarantee you on the test that I will make that an answer choice. So 0.7 divided by 0.2 equals 3.5. I did that earlier, but just let me double check it just to make sure that I'm not stupid. 0.7 divided by 0.2. Yeah, 3.5. All right. So the opposite of that, if I did them upside down, 0.2 divided by 0.7, 0.7, no, 0.2 divided 0.7, 0.285, I would have that as an option. So make sure that you're aware of what you're doing with your math. Though it should be kind of a giveaway if you don't get a number that's, bigger than 1, because that's not really a mechanical advantage. Though it's not impossible, because I told you all some examples of machines that are useful but actually have a decimal mechanical advantage, like tweezers. Tweezers and any class 3 lever, for that matter, definitely has a decimal mechanical advantage. It's not an advantage, it's a disadvantage. You gain more distance at the expense of needing more force. Instead of having it the other way around, you put in more distance to get more force, which is what usually machines do. So if the wedge is 60% efficient due to friction forces, how much actual mechanical advantage, otherwise known as AMA, there's no S, AMA equals what? That's what we want to know here. So the equation for AMA is going to be not what we're looking for. The thing that it gives us is efficiency. All right. Actual mechanical advantage and ideal mechanical advantage are related to each other by this whole efficiency concept. Efficiency not only gives you the amount of work that changes. That was the whole thing that I harped on in class today, was that efficiency is the work output divided by the work input. It's the amount, so the percentage of the useful work that the machine does versus the work that you put into the machine. So the other way to say that, though, is how much of the mechanical advantage that you get, because the other effect of that losing energy is that you don't get all of the force that you actually thought you were going to get. So actual mechanical advantage as a percentage of the ideal mechanical advantage is also equal to the efficiency. Now, quick point here, I didn't have that in the equations before, and I'm going to add it right now. Also, efficiency equals AMA divided by IMA. Now it's there. I'm going to point this out in class tomorrow, or today, depending on when you're watching this. It's on Thursday. I'm going to say it in class. So hopefully I'll have this, now that I've added it, it should be updated on your sheets, so it should appear on yours. If you made a copy of it, it won't appear though, so go ahead and add that if you didn't have it already. So yeah, back to what I was saying. The wedge, the efficiency is going to be equal to AMA divided by IMA. So the equation we want to use is efficiency equals AMA divided IMA. And then I'm going to plug in the information that I know. 60% is the efficiency. I want that as a decimal, so 0.60 is 60%. AMA is the question that I don't know, and IMA, we found out in the last problem, is 3.5. So 3.5. So what I have here is some basic algebra. 0.6 equals AMA divided by 3.5. I want to multiply that 3.5 over to the other side, or more importantly, I just want to get what 60% of 3.5 is. So 0.6 times 3.5 equals 2.1 is going to be our actual mechanical advantage. Bam, that's done. I'm down to 1 minute on the time limit for this video, so I'll go ahead and try to get the other machine problems in the hopefully 4th and final video.